speaker this morning is Samet Oymak from University of Michigan. Samet, you're also a Caltech.
Yeah, from Caltech alumni, yeah.
Featuring Caltech alums. But before that, he was at Bilkent in Turkey.
Oh, yeah, that's right.
And you were at Riverside for a while, and then he moved up to our neck of the woods, so we're happy to have him in Big 10, which is now like 20 or something. Anyway, he's an expert in a lot of things, and in the last few years he's been working a lot with transformers and in-context learning. I've read a bunch of his papers. I'm sure I'll learn something new this morning, so it's Samet. He's got all sorts of awards, just like everyone else. Go for it, yes.
Awesome, yeah, thanks for the introduction, Rob. Yeah, it's a great pleasure to be here. Thank you all for attending. So today, basically, I will discuss some of our recent work on surrounding in-context learning, and my goal is not only discussing theoretical aspects, but also hopefully I will try to motivate why we might care about even the theoretical side, because empirically this in-context learning is also I would say interesting beyond language as well, even if the initial motivation or initial observations are in language. So this talk is primarily based on these 3 papers. One of them is from last year. This one will appear in Colm, and this one is under submission to NeurIPS. And this is there are a few collaborators, but the primary collaborators are Ying Tong, my student. She will be faculty in New Jersey Institute of Technology soon. Davut, he was postdoc at Michigan and UPenn. Ankit is at Google Research, and Mariam is, Mariam. So in fact, Mariam was saying, I might miss the talk and so on. I'm you're not missing anything, because I'm literally talking about the stuff we did. So there's not much to miss for her. So just to give some introduction, obviously, I'm sure many of you are familiar with in-context learning, but it is still good to give some brief introduction. So obviously, we are very interested in transfer learning. Everybody wants to understand, distribution shift or how to deal with distribution shift in general, right? And to do so, there are multiple methods we can utilize, right? One is essentially fine-tuning, and there can be many different fine-tuning methods, like prompt tuning or lowering adaptation, or just SFT with all of the weights, right? And in-context learning is essentially another adaptation strategy, you would say. And the basic idea is that, if you have a sequence model, you can, update the prompt rather than the weights to do adaptation, right? And this prompt update can happen in many different ways. For the theoretical models, we might focus on a certain update rules, but in general, it's pretty flexible. So the advantage of this in-context learning, or basically rather changing the prompt of a sequence model rather than the weights, the advantage is that basically the weights are not updated, right? And it is often, that can make it more robust. In some sense, basically, SFT can be perhaps more brittle unless you have more data often. So in some sense, basically, you are conditioning the output of a sequence model using few set examples, oftentimes. And so this, I would say, basically, it became in-context learning became notable in the context of language modeling. And that might be because basically these initial foundation models, or the fact that basically sequence modeling, in some sense, you need some sequence to condition the model, right? And obviously the first foundation sequence model is language model, right? So in that sense, it became more obvious in the context of language. But if you think about it, right, even if you are doing time series forecasting, and if you get a bunch of data from different time series domains, right? In some sense, whatever time series forecasting transformer you have now can forecast multiple domains, right? You can essentially view even that as in-context learning instance, because in some sense, you are meta-learning across domains. So whenever there is some kind of a meta-learning happening across domains using a sequence model, you can view it as in-context learning. So a typical example could be this, right? So in some sense, my actual query is cheese, right? And I don't know, given cheese, what should the model say, right? It can say anything. It can just smile for a photo, right? We don't know. So we just need to essentially describe the task to the model using the prompt so that it will know the task, right? And in order to do that, we can literally use the task description through translate English to French. There's a proper task description, how to execute the task. We can also give examples of like the tasks so that model can essentially follow the instruction. So in some sense, basically, both of them could be viewed as instances of in-context learning, but this is more like prompt tuning or prompt engineering part, right? Whereas these are kind of like few shot examples, like in the context of like language modeling. And like for our talk, we will mostly focus on these examples, like this, providing the model with few shot examples so that it's conditioned. So, and the high level idea, like if you want to view this from like function learning point of view, right? So we want essentially we want to condition the sequence model so that it essentially picks up some hypothesis, right? So you give these examples like, apple, manzana, banana, platano, and so on, so that like the model will learn the function, English to Spanish, and apply it on the query, pineapple, to get some output, right? Or like, the example can be Japan, mochi, China, mooncake, and so on, and perhaps like Turkey, like the most relevant dessert for Turkey after the country to dessert mapping is perhaps baklava, okay? So we have these in-context examples, and in some sense, basically, we are doing either like, there are like multiple different interpretations, like Bayesian inference or like empirical risk minimization and so on, so that basically we solve this learning problem, like learning a hypothesis problem. To given these examples, we learn a hypothesis from, let's say, English to Spanish or country to dessert, or in general, X to Y, and apply. And this is obviously, needless to say, this ability is related to kind of like algorithm learning, which Nina was talking yesterday. So it is actually pretty relevant also her talk from yesterday, because like we want the model to learn an algorithm at a high level, right? And by algorithm, I mean a learning algorithm that applies on the context examples. So the goal of this talk is basically like kind of like discussing the relation between architecture and algorithms, right? And so in some sense, basically, we can study, like when we think of transformers, like typically we are thinking of like the softmax attention, right? So in this talk, basically, I will mostly focus on actually linear attention and its variants, and how like these architectural primitives can be studied in terms of like certain simple regression tasks, okay? So to give some background on the architectures, obviously, like, perhaps like far time ago, right, we had this RNN and LSTMs, right, before this transformers. And, but in this area of foundation models, right, since 2017, we are dealing with transformers, which is softmax attention based, right? And obviously, transformer has, a lot of strengths in terms of expressive power and the fact that we can build essentially super large pre-trained models. But then it also has like computational bottlenecks, which kind of motivates like linearized versions of attention. It can simply be linear attention, or it can be some kind of like attention after a kernel trick, perhaps to even approximate softmax. And after this linear attention variants, which is essentially like efficient, because you can do like O1 time inference and so on in the recurrent mode, there is essentially like a lot of progress in the linear attention space or recurrent modeling space, because these guys admit like efficient recurrent representations. So there are state space models, such as like H3, and there are also like these gated linear attention models, which essentially spans these Mamba architectures as well recently. In some sense, you're essentially incorporating a gating mechanism in a linear attention type architecture. Like you are still like maintaining linear time behavior or like efficient behavior while enhancing expressivity and selectivity. So, and what I want to discuss, like one thing I want to discuss is basically how these architectures can solve different regression type tasks more efficiently than others. Like there is kind of a hierarchy between them. And throughout the talk, when we say transformers or like transformer type architectures can emulate learning algorithms, what we mean is basically, essentially just like this map from, let's say, country to the dessert, right? We are talking about basically how like model can essentially take the query and apply a learning algorithm over the context window, right? For instance, like perhaps like one simple learning algorithm is like, if my query is X, I want the model can simply go and implement nearest neighbor rule, right? And actually softmax attention is great at this. Like softmax attention one layer can easily solve like nearest neighbor kind of tasks, right? And that would be basically given a query X, go and find the nearest Xi in the context and assign its label to my X. Or like this can be a linear regression type predictor, right? Which essentially like and one point will be that different architectures maps to different algorithms. Like softmax attention can easily implement nearest neighbor, whereas linear attention is mapping to linear regression in some sense. And I should emphasize that there are like many different works, both like studying just like one layer from like one layer attention architectures to like more like, okay, in general, like what is like multi-layer transformers, what they can express, right? Like there are many works in this space which I will not be able to refer to all. So but what I want to motivate is basically like I want to start like this linear attention discussion, which is essentially fairly well understood topic, I would say. I mean, at this point, based on the like what is known in the literature, like it's fairly well studied, and the basic idea is like as a motivation, let's consider the following instance. Like suppose like y and x are related through some function beta, okay? And in the context window, we are using this encoding. Like each token is like some xi yi pair, and we have this x1 y1 blah 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 xn yn. These are the context examples, and we provide x new, and without the label, and we hope that basically model can solve y new if we train it a lot, right? So in some sense, we are solving a meta-learning problem. Model has some weights. Z has a distribution. And the goal is that basically we will optimize the model over this distribution over the prompt Z. And this prompt is essentially distribution of the task as well as the features. So in some sense, it is a joint distribution over beta and xi, right? And the hope is that basically the model will provide the best fit to the y new. Like it will essentially try to solve something from this training data set to predict x new. Okay. And the recent literature essentially focuses on like how like you can construct or even perhaps like sometimes analyze the optimization landscape. And one conclusion, and again for softmax attention there can be a different conclusion, but one conclusion is that linear attention can map to gradient descent type algorithms. Like k layer of linear attention can implement k steps of gradient descent to on these examples to figure out a predictor for x new. Okay, so how does this work, right? In other words, like what is a specific model? Just to give some concrete setting, right? Let's say my model is simply a one-layer linear attention. It is like kind of like as simple as it gets in terms of a sequence model, right? And one-layer linear attention looks like this. So I have a prompt Z, and one-layer linear attention can have weights W and V. So W is the key query weights. It is a key query matrix, and V is the value weights, okay? And the model outputs given from Z, the model computes a third order polynomial of Z, ZW, Z transpose ZV, where like ZW, Z transpose is the attention map without the softmax, and ZV is the values, okay? And then it computes output, and from output I can just read the final token to read my prediction, and that's my y hat new. Okay, and then in the simplest model, we can assume that data generation is such that like there is a distribution on beta, perhaps Gaussian, and there is a distribution on X, perhaps again Gaussian. Okay, and in the simplest model, they are all independent. So basically our goal is kind of like taking this setting and discussing like generalizations of it and what it means for different architectures. So this is kind of, I mean, what I described earlier was an example of this simple regression task. I mean, it's not like that simple because there's a meta-learning going on. There is a distribution on beta, but it is still, you are simply solving a linear regression after you settle on the fact that you just want to learn a beta, right? So this basic regression task could be like this. In fact, you don't even need under certain conditions, you don't even need a linearity assumption. I mean, you would just like learn the best linear predictor basically. I mean, depending on the setting. But we can essentially spice up this setting. Like, I mean, we have this like purely linear setting, right? We just described here. Like all these examples, xi's are all related by the same beta, right? We can easily spice up the setting to consider as following scenario, right? Perhaps like my context window, which is pretty relevant for language. Maybe it is a mixture of multiple tasks. My context window is not like single beta where everyone is related to each other. What if like there are multiple betas in the context window? Like which is perhaps more relevant for like language, right? Because in language, the whole point of softmax attention is that you want to pick up what is relevant or not, rather than like equally weighting everyone. And another example that we will consider, like kind of like mixed regression setting. Context is heterogeneous, or it contains many tasks. Another example is like what if basically perhaps like labels are missing or labels are noisy, right? In that case, basically what kind of like algorithms the model can emulate. This can be another example that I want to discuss, yeah.
Mixed regression, like often there it would just be at each time you pick one of these betas randomly, whereas as you described it with language, it might be like, oh, you're running with this beta for a while, then you switch to that beta. Is there any structure in your extra structure beyond the usual mixed regression setting?
Yeah, this is exactly what I will discuss. So basically, in the mixed regression setting, indeed, betas are changing in the context. In other words, in the same context, betas are changing.
Is there a little run of beta, this beta? Is there any structure?
Oh, yes, we will get into that actually. I mean, this is a great point, yeah. So what I want to discuss very briefly is basically how does like I mean, here is kind of a very summary of our some of the results, right? So in some sense, linear attention can be mapped to preconditioned gradient descent, and this is a fairly well-known result in the literature, basically. So in some sense, like when you optimize a linear attention, one layer, I mean, many of these results are for one layer or expressivity results, okay? Or like perhaps like sometimes stationary point results. But at least in the context of one layer, when you optimize a linear attention, you eventually end up learning a preconditioned gradient descent predictor, where what happens is that basically your key query weights W essentially applies a whitening function or like some kind of like transformation on your features to construct a beta hat, and you use that beta hat to predict, okay? So it turns out, basically when we study essentially state space models, what we can show is that basically if the context window is homogeneous, it is exactly the same as linear attention, there is no difference, but if the context window is heterogeneous, in the sense that if there are different betas, right? I mean, there is a final beta, and they have different levels of relation to your final beta. In that case, state space models can prove like their landscape, one layer, ends up learning a sample-weighted preconditioned gradient descent. In other words, it is kind of a richer class of learning algorithm in some sense, right? And this sample-weighted means that you are transforming the features with this key query weights W, but you're also able to weight the individual elements of the context to create an optimal predictor for your beta. I mean, to obtain a better estimate of your beta. But like one potential weakness of state space model is in some sense basically they are not adaptive. They are not adaptive to the data. And by adaptive, I mean basically these weights that state space model constructs, they are essentially fixed. There is a fixed impulse response. And fixed impulse response is bad for business, especially in the context of language modeling. Because it assumes that the relevant information is always at a fixed point. Let's say the nearest point to the query, right? Which is not reasonable, right? So when we essentially study these gated linear attention architectures, what we can show, and this is like a little bit abusing the notation and so on, is basically these can essentially learn sample-weighted preconditioned gradient descent, where basically this omega is data dependent. So basically, in some sense, basically, state space model is learning a fixed omega, right? Whereas gated linear models, like because of the gating mechanism, which weights the context based on this gating structure, it is able to learn a weighting which adapts to the x and y, right? And obviously, like, you know, this analysis of this gets messy and it requires some assumptions and this and that, but this is kind of the high level, perhaps like hierarchy.
When we talk about these sample weighted solutions, should I be thinking like beta is like some linear combination of the context that you put in, or like I'm trying to build some intuition for what the sample weighting buys me?
Sample weighting buys you? Yeah, so basically imagine, I mean, so in the context of language, it just simply means that basically perhaps like some tokens, some words are not related to you, right? I mean, maybe you are trying to prove something and you know that there are some totally unrelated lemma that you don't want to use, right? So in this context of this linear, and we will get into more details if time permits, but in this context, it simply means that there is a final beta, which comes from a distribution, right? And in the context window, there is another beta k, right? And that beta k might have very low correlation to your task beta. So if you know that basically the correlation level is low, right, you want to weigh it lower because that beta k task does not help you estimate your target function.
I guess I would have expected the weighting to depend on this little x. Like you had the little x in the context, and we have x1 for x and y1 for y in context. Somehow little x tells you which of the in context training examples are.
Yeah, actually that's a great point. So it does depend on the little x in some sense, but actually I can add the little x here. That's a good point. But it also depends on all of the other guys. And the reason it depends on all of the other guys, basically, yeah.
So there should be a little x.
Yes. There should be a little x. You're totally right. Yeah. But the reason it depends on everything else, unlike let's say softmax, is because when the gating hits, right? It is because of the recursive nature, basically. Yeah. And finally, like in the context of, let's say, suppose we have unlabeled data, right? And in this case, basically, what you can essentially show, and again, these are kind of constructive arguments. Like, there is some other point I want to make for unlabeled, but what you can show is that basically these attention models can naturally implement iterative pseudo-labeling, right? In the context of linear attention, basically, there is better connections to kind of spectral estimation in the sense that basically, rather than just trying to use X transpose Y estimator, right? If your data is, let's say, Gaussian mixture model structure, then the model can actually benefit from this X transpose X estimator, like to, let's say, estimate the top eigenvectors and so on. Okay. Yeah. So this is essentially kind of the summary of what I wanted to discuss, right? And there are a few things I want to discuss, but this is kind of the high level. So the next thing I want to discuss before I proceed with more detail is why we might want to care about in-context learning beyond language, right? I guess this from my point of view, this thing got more popular in the context of language, right? But in terms of application, actually, I'm more excited about applications in structured data or time series forecasting and so on. So in some sense, basically, the claim is that this using transformers or general sequence model for we can use them for broader statistical inference, just rather than saying, okay, here's a bunch of language examples. We can actually use it on structured or classical machine learning tasks. So basically, the high-level opportunities that we can use essentially foundation models to meta-learn from huge number of tasks. And by these tasks, I mean classical, this UCI or Kaggle competitions and so on, right? And even the encoding, right? So for instance, when we are discussing this linear attention encoding, each token has some XI features and some YI label, right? We can even keep similar encoding, basically. In other words, we don't need to encode this language model in order to use them. We can actually use just raw feature encoding to, let's say, solve this adult data set kind of thing where we are trying to predict someone's salary. So perhaps one surprising question can be, okay, can in-context learning with a suitable transformer beat XGBoost or light GBM, right? Because when you are doing this Kaggle type competition, the go-to methods are often gradient boosted trees, random forest, and so on, right? And it turns out, they are at least competitive, especially in the context of small data sets, right? There is a lot of progress happening in this space where it is more and more clear that especially if you have a small data set, right? On structured data or classical machine learning task, in-context learning with a transformer can actually beat this XGBoost and light GBM or bunch of other classical techniques. And here, small data is important, in the sense that with large data, perhaps you can construct very good approximators, right? But with the small data, you essentially get this meta-learning benefit, right? In some sense, you have a model that learns from insane number of priors, right? So that when you condition with the small data, it can do a better job than trying to tune small data from nothing. And this is an example grabbed from this is the top PFN folks, right? Frank Cutter and his group. And they're essentially demonstrating here that basically, top PFN, which is essentially you just plug your data set in a transformer, pre-trained transformer, can potentially beat like fairly well fine-tuned XGBoost like GBM models under a small data set. And again, even the context of basically time series forecasting, I would say it is similar, because like there's not too much difference between like time series forecasting and structured tabular data, right? Because essentially you have a time series and you can either create tabular features or you can treat the time series as a tabular forecast, right? Where like your y is just the next value. And people are also, I mean, I'm just showing my own paper, but like there is a lot of interest in like building time series foundation models, which can also be viewed as an instance of in-context learning. Because you are essentially learning, meta-learning from many tasks, and you are trying to do zero-shot or few-shot forecast. Okay, so I just want to mention this like simple idea on like this revisiting gradient descent, right? In the context of like, let's say gradient descent with one layer attention, what's happening. So let me see this. Yeah, so basically this is how it looks like. So in some sense, we will essentially map this linear attention to gradient descent, and as we discussed, like state space models to this like sample weighted PGD, right? And what I want to discuss is basically like how what is the basic idea? What is the basic intuition when we are relating linear attention to preconditioned gradient descent? So this is kind of what I want to discuss. Just to give some high level idea on like what is the basic proof idea. Like, and this is not our work. This is like earlier works. So we know that basically output is basically this ZW Z transpose ZV. It is essentially a third order polynomial of Z, right? And the first observation here, and we are reading the final entry of out, which is essentially we will read the model output at the n+1 coordinate. And the first observation is that basically y hat new, the prediction is already in the form of x new transpose some very modified W Z transpose ZV. So prediction already has this x new transpose in it, right? And the remaining question is what's happening to Z transpose Z? And Z transpose Z itself, I mean, this whole thing can be viewed as your beta hat, right? In other words, it will provide you your beta hat that you will predict. And and the question is basically in terms of optimization landscape, why does it have to be in the X transpose Y form, right? Because, it can be X transpose X, Y transpose Y, or X transpose Y. In some sense, there are not too many options that it can be. And the reason, at least one obvious reason, depending on the assumptions on the data, one obvious reason it should be in the X transpose Y form rather than some other form is the fact that basically, suppose beta and Xi are zero mean and independent, right? They're like, suppose like IID Gaussian type distributions, right? So, and we just look at basically whether Y hat new can predict Y new. So if we just look at Y new and Y hat new, right? Obviously we want some non-zero correlation to get some prediction, right? So in order to get a non-zero correlation, this should better be an even moment of beta and Xi, right? Because as long as you get an odd moment, you would just get zero mean. So this means that basically Y new is a second moment because Y new is beta transpose X. It is a second degree polynomial of beta and X. So Y hat new should also be a even degree polynomial, right? So then the point is that basically if you use, let's say, X new transpose X transpose Y, this is a fourth degree polynomial, right? Because it is X beta, fourth degree. Whereas if you use X new transpose X, it is useless because it is third degree polynomial. You will not get a prediction. I mean, under the assumption that Xi's are zero mean and like everything is zero mean and independent. Okay?
Sorry, I lost track of the notation. What is V?
Oh, V is the value weights. So yeah, V is another matrix of size. It is a vector of size d+1. So in some sense, basically this thing is like it projects. So this computes the let's see. So this ZW Z transpose is the attention map. It is like n by n, whereas Z times V is the value weights, and then you essentially multiply the attention map n by n with n by d or n by 1 values. So in this case, label is scalar. So as a result, V has to be a vector of size d. Yeah. Yeah, essentially this kind of this moment tracking argument, right? And I mean, obviously, when you're analyzing optimization landscape, it is messier, but this is kind of the high-level idea on why, like, you will not get X transpose X term or some other terms. Like, X transpose Y is the natural thing you will get. But if you had a Gaussian mixture data, that's different, which we will briefly discuss. So basically, this linear attention motivated state space models. And one reason for that motivation is that this linear attention with causal mask, so not like standard linear attention, but if you also add a causal mask so that it is autoregressive, it has a recurrent formulation. I mean, it's classically well understood, which is what makes it efficient when you are doing autoregressive decoding. And since linear attention are RNNs, which is literally a paper title, so then this motivated like further research into basically this recurrent formulation linear-like models, which is essentially state space models, which primarily it is like developed by Crisra and co-authors, like among others, obviously. So we essentially picked one state space model, which is the like arguably top performing state space model, which has a fairly similar structure to linear attention. And so this model is, rather than using attention mechanism, it is essentially using these entry-wise products. Okay? But eventually the interesting thing is that when you essentially analyze the landscape of this entry-wise products is literally equivalent to attention in terms of the optimization landscape. I mean, that was one interesting conclusion. Essentially, this is the convolution, where convolution is basically impulse response of the state space they put, right? And they are using entry-wise products rather than attention, which is the similar intention, right? Because they are literally using query key volume matrices, right? But once you analyze the optimization landscape, all these matrices collapse, QKV, in a very similar fashion to how linear attention collapses. And you literally get the same thing. You get the same solution where SSM maps to a preconditioned gradient descent, with the difference being you are essentially weighting your samples using the impulse response. So in some sense, they're able to adapt the weight depending on like where you land in the context window. So overall, basically, like one conclusion is that under some general condition independence model, we are showing that as long as basically from the query's point of view, everyone else looks similar, then linear attention is exactly the same as SSM in the one layer I'm talking about, in the optimization landscape, because there's no need to weight anything, right? I mean, all the context looks similar to the query. In that case, everything is equal. And we can characterize, and one additional benefit we obtain in this analysis is that unlike previous work, which assumes like independence of like beta and X, we can allow for correlations. And I will skip over this quickly, but so in some sense, basically, you can ask questions like, what if like task vector is very correlated to the query, right? Perhaps features and task is correlated, or there are a bunch of other different correlations. So one nice result regarding this correlation is that if there are correlations in the context window, and I will not get into exactly how the correlations, but the most obvious one is like beta and X are correlated, right? Then actually in context sample complexity reduces quite a bit, which kind of makes sense. In other words, the more the correlation, the better the model can utilize the in context samples, because it is just giving more information to you. But going back to linear attention versus SSM, like one thing is that, okay, like if they are all looking similar to the target task, they are equivalent. But if I can essentially modify my context window in a smart way, if I believe that, let's say, recent tokens are more relevant for my language task, then things are different. Actually, in that case, basically, indeed, SSM can probably be better than linear attention, just because of the fact that it can weight the context window. Yeah. So I just want to briefly motivate this question, which was actually like one of the like which was kind of exciting to me. So like we are discussing this like weighted preconditioned gradient descent, right, as an algorithm. And like one natural question was basically, what is the optimization landscape of WPGD in this like sophisticated scenario where there are different betas, okay? So I guess the question is this, which is again going back to the yesterday's like algorithm learning discussion, but this is kind of a not statistical learning question, but more like optimization landscape question, okay? And the reason I like this is because like I like, let's say, low rank factorization or bilinear models and so on. So this ends up becoming something like this. So imagine the following, right? Imagine you have a prompt, or imagine you have some x and y. You have a x features and y features, and you have a x new, and there's a distribution on them, okay? And the question is basically learning, the question of learning what is the optimal weighted precondition gradient descent algorithm. And if you fix one of them, if you fix omega or if you fix p, this expectation is essentially a linear regression problem. It is a linear problem, right? But if you study both of them, actually it becomes more interesting because it is like, bilinear kind of problem, right? Or biconvex problem. Yeah. And this is an algorithm learning problem. What I liked is basically this is an algorithm learning problem while having this matrix factorization type flavor, basically. And obviously you can study this in population or in empirical risk and so on. And empirical risk will be much more complicated, which we didn't do. But overall, we have some results on this. And our result is that basically, we have a technical setting. And basically, the technical setting was, okay, like we assume xi's are, let's say, independent. And they have a covariance. But the critical thing is tasks are correlated. They have a covariance. Like this beta i's have a covariance between them. And the final task beta niv has a correlation, cross covariance to all other tasks, which is exactly the relevance setting. Like my final task has different relevance, and all other tasks can have their own internal correlations, right? So under this setting, this optimization landscape is related to basically R, which is the task covariances, feature covariance, and also cross covariance, like in terms of three things. And we want to learn this. And essentially, like this is messy, but we have a theorem which essentially characterizes stationary points of this problem, algorithm learning problem, in terms of basically some fixed point equation. And this fixed point equation is coming from the fact that like omega and p are coupled. So when you solve that coupling, you essentially can reduce pretty much everything to scalar fixed points, but those fixed points depend on the eigenspectrum of sigma and R, okay? So, and the conclusion is that basically we have this we can obtain a fixed point equation which is H1, H2, gamma plus 1. Yeah, so basically, if essentially we just need to solve for gamma, which is equal to H1, H2, gamma plus 1, fixed point of this equation. And those are the gammas that can be that essentially returns you the stationary points of the optimization landscape. So in some sense, like under certain conditions, which I didn't list all the assumptions, we can characterize the optimization landscape through at least the stationary points. I will skip over this, but and if you essentially simplify it, so like one simple theorem is that if the spectral gaps of these covariances are small, then actually there is a unique stationary point and global minima. For instance, if the covariances are just isotropic, then like you know exactly what is the solution. So the weighting will be like flat and so on, basically. So this is like not exactly sequence model related, but it is kind of this landscape of algorithms kind of question. So yeah, so one thing, and just to wrap up, like I'm coming to the end of the talk, hopefully. So obviously, like one problem with this WPGD is the fact that like we are using a fixed weight vector, right? Which is also the problem with state space models, because like I don't want just temporal understanding. I want like data dependent understanding, right? And so this kind of essentially motivates this gated mechanisms, right? And this gating mechanism in the context of linear attention is just this. So we have this linear attention recursion where like state is given by state plus key value transpose, okay? So when you add gating, you are essentially adding a GI function which essentially controls the state. It can essentially erase the state so far. So it is essentially a recurrent, it essentially makes the model recurrent with selectivity, okay? Rather than adding everything to the state, always storing key value in the state, you are able to sometimes erase it or control part of it. And this gating function can have different levels of complexity, like which results in different levels of expressivity, which I will not really discuss, but many of these architectures that are trying to replace transformers, or at least like provide efficient alternatives, they can be viewed as a gated linear attention, like in some sense like recurrence with some gating mechanism. And the way this gating mechanism, I mean, this particular structure is also important because like, it still allows for efficient inference and efficient training. Okay, so overall, basically, what we can say, I mean, this just comes from like more or less just like studying like what is going on basically. I mean, this is not like particularly sophisticated result or anything, but overall, like you can essentially view this gated linear attention as a data-dependent weighting procedure, where these weights omega are essentially recursive multiplications of the gates, right? And this gate depends on all of the history in some sense. Okay. And like in order to study this, obviously studying this gets very messy, especially optimization landscape and so on, and I will not get into details of it, but at least our approach to get some kind of preliminary result was like decoupling. The idea was decoupling features and gating function, because features influence the gating, features also influence how you learn a predictor beta head. It just gets too messy, okay? So rather than that, we essentially created this like contextual model. Like in some sense, it's kind of a fake model which tries to isolate the impact of gating from this learning beta head, okay? And the idea is that basically suppose you have documents, document 1, document 2, document 3 in the context, and between each document there is essentially a delimiter. And this delimiter, when we apply gating on this delimiter, we have this option to decide how much to forget based on this delimiter. So through this delimiter, we are able to decouple essentially what is gating doing and what is in-context learning doing in some sense. I mean, I will not get into the results, but this is the high level, like the high level thing we tried to formalize and like get some kind of landscape results. And in terms of the essentially in terms of the some simple experiments, indeed what we can verify is that like using this gated linear attention model, right? Like contextual features actually help, and like using this gated linear attention model, you are able to match weighted PGD even without knowing the locations of where is the important information. In other words, even if you shuffle the information document order, the model is able to kind of pick up this contextual relevance. Yeah, this is a bit vague, but you know the high level idea is basically like data dependent weighting through this gate mechanism. And the final bit I want to discuss very briefly is like this like unlabeled data aspect, just because like it has different algorithmic interpretation. Because so far we have been discussing like this as if everything is gradient descent or so, right? So, but the reality is obviously if you change your data model or if you change your architecture, then you end up with something different. Like in this case, like we study a Gaussian mixture model, which is a clusterable data, right? It's not like isotropic data. It is a clusterable data. And some of the examples are missing, like some of the labels are missing. And the first observation is that, again, if you study the landscape of linear attention, actually what you find is that basically in the context of Gaussian mixture model, linear attention does the optimal estimator. Like the base optimal estimator under a suitable assumption, like isotropic task prior assumption is like simply X transpose Y. That's the best estimator you get, basically. And linear attention learns that. But the conclusion is that linear attention does not utilize any unlabeled data, right? Because if you are learning X transpose Y, and if Y's are padded with zeros, obviously there is just not enough room to do anything unlabeled. Like you don't get any benefit from unlabeled. Whereas this is just observation. It's not even any theory or not. If you just think about what the attention mechanism is doing, right? In some sense, like attention map times stuff, right? The attention mechanism itself is naturally just like imputing missing labels or essentially propagating information from neighboring tokens to you, right? So if you have a missing label, suppose I have a missing label 0 here, one layer of attention can essentially impute myself, right? It is 0 gets 0 plus attention weighted combination of non-zero labels. Like if you essentially do this model of X, Y, and you only write on the Y's, I mean under very mild assumptions, what attention is doing is basically it just takes information from your neighboring tokens and just like put it to you, and also takes information from you and put to others, right? So the attention mechanism itself is like doing some kind of natural imputation. Even one layer is just doing imputation basically. And if it is multi-layer, then it is just updating some belief. So when we study this linear attention, what we end up finding, I'm almost done, is rather than doing simple supervised estimator, which is X transpose Y, a multi-layer attention actually can do like semi-supervised estimator, where you are doing X transpose Y, which is the supervised estimator, plus a spectral estimator in some sense. In some sense, this is what you can eventually approximate, right? And the spectral estimator is basically not only using, X and Y correlation, but it is also grabbing the mu estimate, in other words, the task mean from the, let's say, by emulating some kind of top eigenvector. And this also has some kind of a expectation maximization interpretation, because like you are taking mu and then hitting with X to get some labels, and then you are using that labels to get mu again, and so on. So one observation we had is that, like in this previous discussion, the amount of polynomials you can construct if you just update the labels is just linear, in the sense that you get like to the degree L at the Lth layer, right? But the reality is that basically a linear attention model can actually construct extremely high degree polynomials, because every time you can multiply your degree by 3, right? Like the first layer is like 3rd degree polynomial, second layer can get 9th degree polynomial by computing the 3rd degree of the first layer. So long story short, basically, indeed, like you can construct like you can quickly estimate spectral estimator by very quickly constructing very high degree polynomials of X transpose X. And this is also what we see empirically. Empirically, basically what we see is that these models can actually need very few depth, not very deep, to get like decent semi-supervised learning performance. So basically, in fact, logarithmic depth can suffice. So perhaps like I can skip the future directions and take questions, and then if necessary, we can go to directions, yeah. Thank you.
You mentioned the mixed regression, and still, I didn't see that come up later exactly. Is that, what, yeah.
Oh, yeah.
And I guess I'm just trying to even understand the setup there. Is this one of those situations where there's correlation or dependence between the X's and betas? Like,
yeah, actually, I would say the mixed regression, the main discussion I made was over here. But by mixed, I mean the context window is mixed, right? So I think this is the most relevant discussion, I think. Yeah. So in some sense, in the context window, there are n tokens or n tasks. Each task has a beta I, and these beta I's have a covariance matrix between them.
And is there dependence between the generation of X's and betas?
No, X's and betas are, let's say, independent, but betas are related to each other.
Just the betas.
Yeah. Again, perhaps I didn't use the precise technical term for mixed. I just meant that basically context window has different like tasks. Yeah.
And so is this a case where this, omega or whatever is data dependent?
So omega is not that. So in this case, if the correlations are fixed, then things are good, because you know exactly where most correlated task is. Whereas if you shuffle, suppose at test time you shuffle these, then that same omega will not work. But in the second discussion, which I don't discuss any technical detail, but if you essentially have some kind of a contextual understanding of like, okay, like this beta, I can grab and understand how correlated it is, then I can use gating to pick it up better. Yeah.
Go ahead.
In your last slide, in the context of this unsupervised learning, this multiple layer transfer, I have two questions. One is like, what do you mean by spectral learning there? And also like when you are saying that the performance is like similar to that of like some EM algorithm, right? So does
Yeah.
the last slide.
This one? This one, right?
Yeah.
This one. Yeah. All I mean is the following, right? So in some sense, like if you want to use unlabeled data, right, especially in the context of, let's say, simple Gaussian mixture model, what you can do, the one way unlabeled data can help you is like they can get you the plus mu and minus mu, right? Suppose you have a very symmetric Gaussian mixture model. Even if I don't know any of the labels, if I have infinitely many of them, and I can just construct the covariance and look at the top eigenvector, that will be either plus mu or minus mu, right? So that's the information that I can have from unlabeled data. One example information I can have from unlabeled data. Whereas with supervised, I cannot precisely estimate plus mu minus mu direction, right? So this is essentially kind of a mixture of supervised and spectral-like estimator, because it is essentially using supervised estimator plus using unlabeled information and trying to find the direction of it. And then you can tune this alpha optimally. And when we do this, basically we are seeing that even if linear attention is not maybe exactly doing this, it is approximately doing this as soon as the number of layers is like very like few, yeah, but not one, because one means nothing. Yeah, sure.
Okay, well, let's see some.
Thank you.